The study of squeezing unstable and nanofluid flow due to the radiant heating and thermal generation/absorption. Abstract. In this study, a numerical investigation of squeezing transient nanofluids flow between two parallel plates are considered. The impacts of radiant heating and thermal generation/absorption across the temperature profile were scrutinized. The Runge-Kutta fourth-order method, RK4, with shooting scheme was used to solve the two-dimensional nonlinear momentum and energy equations. It is perceived that incrementing the radiative parameter results in a decrease in the temperature profile, while the fluid thermal reading is vividly ascending in the cause of thermal generation but diminishes in the cause of thermal absorption respectively. The result shows a fascinate and reasonable agreement between the nano-sized and, though, a slight high upturn in thermal boundary layer thickness width is spotted than that of keywords nonlinear equations, parallel plates, ODES, Runge-Kutta scheme, RK4. List of abbreviations. IVP initial value problem. ODES ordinary differential equations. Ham homotopy analysis method. 1. Introduction. Substantial functioning thermal transport fluid models are the topic of numerous scrutinization in current decades. Due to the esteemed thermal conductivity's properties of metals, the thermal conductivity of suspensions of gritty solid in liquids have been an exciting research field for its enormous extent of physical instruments in many industrial and engineering processes. Many publications illustrate the present and prospective utilization of nanofluids. Sale, ETAL, 2017. Nanofluid has diverse applications in engineering and geophysical sciences. Among these comprises cooling of nuclear reactors, cooling of electronic equipment, and solar energy collectors, etc. The flow of fluid and thermal transport via an unbounded upright plate has vast applications in science and technology, amongst which involve packed bed storehouse tanks and catalytic reactors, etc. ETAL, 1991, have analyzed the problem of nanofluid flow across an upward plate in the proximity of time exponential temperature on the boundary. Their result shows that the nanoparticle concentration improves for fluids with little thermal conductivity while the fluid temperature is reducing. Some rich number of studies in relation to the nanofluid flow with different solid particles via indistinct geometries were found in Chamka, 2002, Domavathi ETAL, 2005, Salma ETAL, 2012, Gaylambaz ETAL, 2019, Raza ETAL, 2019, Kumar ETAL, 2019, Chamka ETAL, 2019, Takreye ETAL, 2020, Molina ETAL, 2020, Dagonki ETAL, 2020, and Nirmalan Do ETAL, 2021. Sheikh Holslamai ETAL, 2013, intensively carried out their research in relation to the squeezed unstable fluid flow using fourth-order Runge-Kutta, RK4. Nonetheless, some other fascinating and associated study is detailed in Hamza, 1991. A scintillating research on the radiant heating was conducted in Kandasamy ETAL, 2013. Radiations perform an important task in heat transfer. As such, many researchers have carried out pieces of research on it. Hayat ETAL, 2013, have presented radiant heating impact in squeezing flows of Jeffrey fluids. Al-Sidi ETAL, 2012, studied the thermal generation/absorption impact within the standstill fluid flow. Hussaini ETAL, 2018, examined bioconvection model for squeezing flow within likeness plates bearing gyrotactic microorganisms with the influence of radiant heat and thermal generation/absorption by using HAM. Moreover, the impacts of thermal generation/absorption were sufficiently examined and reported by Srinivasa and Eswara, 2016, Abdelwad ETAL, 2015, and Madaki ETAL, 2018, respectively. The goal of this study is to use Runge-Kutta fourth-order method, RK4, along with shooting technique to procure the numerical solution of squeezing unsteady, 3-4 and 2 nanofluid flow in the presence of radiant heating and thermal generation/absorption. The radiant heat as well as thermal generation/absorption effect were analyzed on the thermal profile. Conversely, the numerical result obtained for missing parameters 0, 0, 0, 4, 3, 4 were compared with previous result obtained by Madaki ETAL, 2018, using fourth-order Runge-Kutta with shooting technique for CU water. 2. Description of the problem. The behavior of unstable nanofluid squeezed within two evenly spaced plates were perceived in this research. The space within the two plates at any dimensionless time t is stated as equals plus or minus 1, 12 equals plus or minus h, where is the distance, is constant, and is original ground, at equals 0. The flow model is deliberated along x and y axis and z is the axial correspondent which is studied to be 0 from the flow province. The viscous distribution influence and thermal source due to friction were fastened. The Runge-Kutta fourth order, RK4, with shooting scheme will be utilized on the modified nonlinear odes to examine the impression of both radiant heating and the thermal generation/absorption along with other parameter on the estimated solution of unsteady squeezing of Fe304 and Ti02-Nanofluid flow within the two parallel plates. Hence the fluid is nanofluid which comprised both ferrofluid and Fe2, where U and V serve as the velocities in x and y guidance, sequentially, whilst 8, and are the pressure, the fluid temperature, an outline temperature, the fluid, the density and the thermal generation/absorption coefficient, respectively, and, and, are appropriately the effective density, dynamic viscosity, heat capacity, and thermal conductivity of the nanofluid as expressed by Uri and Aziz, 2009. The effective dynamic viscosity of nanofluid is given by, equals, 1, 2.5. Where is the solid volume fraction of nanoparticles? The effective density, thermal diffusivity, and the heat capacitance of the nanofluid is provided as, equals 1. Plus, equals 5. Results in discussion. The maturation of the mathematical representation of the compressed unstable nanofluid flow via the equidistant plates as manifested in Fig. 1, where the significant impact of the radiant heating and the thermal generation/absorption variables beside an appropriate parameter on the flow and heat transfer peculiarities have been analyzed numerically. We have used the Runge-Kutta fourth order with shooting method to solve the corresponding governing equations. Consequently, the missing parameters 0, 0, 0 have been reckoned, where both the velocity and temperature profiles were analyzed and they were secured using RK4 scheme with shooting technique as presented in Table 3. From Table 2a and 2b it's observed that the increase in heat generation parameter initiate a slight increase in the temperature profile, showing that for both 2 and 3/4 the fluid temperature is proportionally and physically rising with heat generation parameter, and it is also observed that there is much rise of the fluid temperature with 2 water than 3/4 water. Table 3 depicts the comparison of result obtained by Madaki et al. 22 of Cu water in the present study, 3/4 water. With equals 1 equals 0.5, equals 0.010, equals 6.20 equals 0.020 equals 0.010 equals 1.5, the result shows a convincing agreement between the value of the missing parameters 0, 0, 0, of Cu water and 3/4 water, respectively. In figures 2 and 3, it's observed that both plus and squeezed characters have dissimilar influences on the velocity profile. The squeeze number shows the movement of the plates, which implies when 0 it matches with the plates traveling independently, whilst 0 it relates with the plates progressing jointly. However, it shows that both 3/4 and 2 have mutual agreement with the motion of the plates. Figures 4 and 5 show that for both 3/4 and 2, as the magnitude of nanoparticles is added into the traditional fluid, this gives rise in thermal boundary layer thickness. It is noticeable that on growing in the values of volume of solid particle the velocity boundary layer is leaned near the proximity of the plates, while remote from the surface of the plates it progressed. Owing to the great thermal conductivity of the solid particle, the heat transfer is believed to have been improved, while the thermal profile is anticipated to have been declined. It is also noticed that the rise in thermal boundary layer thickness tend to occur faster with 2 than 3/4 when the parameter is being increased. From figures 6 and 7, the curves show that the fluid temperature is significantly reduced with a bit increment in the radiant heating integer. For every value of, as well as the thermal boundary layer width that is heat transfer coefficient continuously decreases. Meaning that, the nanofluid temperature profiles are influenced by radiant heating integer. For the fixed values of governing parameters. In figures 9 and 10, the curves exhibit the heat source influence on the thermal profile. It is observed that with 0, implying heat generation, there is increase in the fluid physical temperature. While with 0, implying heat absorption, there is decrease of the fluid physical temperature. The effect of heat source parameter gives a similar behavior with both 3/4 and 2 as solid mechanisms. 6 Conclusions. The RK4 scheme along with shooting technique was employed on the modified nonlinear odes to investigate the impacts of both the radiant heating and the thermal generation/absorption on the estimated solution of squeezed unstable nanofluid flow within two equidistant plates. The water-like regular fluid end, 3,4 and 2 as the solid nanoparticles were considered and analyzed. The non-dimensional velocity and temperature outlines have been studied. Moreover, it is quite ostensible that the moment nanoparticles are being augmented into the fluid, the heat transfer is enhanced, due to their great thermal conductivity feature. Thus, the desired and fascinating results were achieved numerically and graphically. The influences of all the prominent parameters concerned have been reviewed and exhibited thereof. The impacts of all the pertinent parameters present have been reported and presented both in tabular and graphically. Competing interests. The authors declare that they have no competing interests.